Okay, thanks everyone. Happy to be here today. Lots of really good discussion. I was able to sit on a couple of the sessions before this, so obviously there's clearly lots going on for AI and for Gen AI in both the ADAS as well as the smart cabin, or you may also hear me reference the IVI, the in-vehicle infotainment system. So the exciting news for us, so I'm with Micron Technology. We are by far the leader for memory and storage going into the automotive industry, as well as some tangential industries that are related, such as the industrial and the consumer, where we're focused on some of the AR, VR opportunities. So in that space, we actually get to work with the OEMs, we get to work with the tier ones, we get to work very closely with the SoC vendors, and so we really get to see the pipeline in terms of the technology that's coming in. All right, so we're going to talk a little bit about hardware. We're certainly going to talk about some of the system requirements and what's trying to be done from a user application or from a vehicle functionality perspective that's driving a lot of those. And ultimately, you know, that memory and storage is a key piece of the technology enablement to be able to do the things that we want to do in the vehicle. At the same time, it can have sometimes unintended implications that really need to be considered. I know there was a question earlier about some of the system implications of battery management system. And surprisingly, one of the things that's not necessarily front of mind, as an example, Sentry mode, when the car is essentially in standby, one of the biggest impacts on the vehicle drain is the memory and storage that's still essentially on and being used to monitor that system. And it can have a meaningful impact on the order of roughly 1 mile per hour that it's in Sentry mode. And if you think about that over a 24-hour day with maybe 20 plus hours in Sentry mode, right, these kinds of choices in terms of what memory, what storage is the right application can have that much of a difference in the ultimate end user experience. Okay, so as I mentioned, we're going to talk about both AI, which is already in vehicles today for the ADAS systems. We're also going to talk about Gen AI, which is obviously coming into the smart cabin. And it is there to some degree today already, but most of those implementations, almost all of those implementations are essentially still utilizing the cloud. It's not local in the vehicle, but that's absolutely coming, both because the technology itself is going to enable that, as well as some of the advantages of doing it locally. And specifically here, you know, some of those advantages of doing it locally are the items such as privacy and security. And in fact, in some parts of the world, this is being legislated and or will be legislated in terms of certain Europe and other places that tend to be very sensitive in terms of privacy and security of end user data. Latency is a big one, right? So again, the time to the response, that overall user experience is of utmost importance, really can make or break a technology. And so that latency, being able to do that locally there on the vehicle, just tends to provide better quality of service. In some cases, utilizing the cloud is absolutely no issue, but there are those corner cases where it does become an issue. And we've all been frustrated as consumers in certain cases where technology runs slow, so we don't want the end user to have that experience. Connectivity is another one, right? So again, connectivity can be spotty in certain places, just depending on where you are, especially countries such as the US, where we have such a spread out terrain. And fundamentally cost, right? So this was more of an inhibitor previously, but if we think about both the compute power that's coming from the next generation SoCs, as well as you'll see here shortly some of the memory and storage bandwidth capabilities are hitting cost points that now make it feasible to do that locally in the vehicle. Okay. Now, of course, for automotive, we also have to think about some of the things that came up earlier. We have to think about cybersecurity. We have to think about quality. We have to think about reliability. And all those can be enhanced with automotive-grade experience and automotive-grade components that go into that system. At a high level, if we think about how a Gen AI request comes into the vehicle and is utilized, you can see a fairly simple pictorial, which is there's typically multiple models that are stored in the storage, which is typically NAND technology today, an SSD or UFS type of device. And For some folks, this is actually the first realization that there are multiple models in this space. So, for example, there may be an initial model that does the talk to text or talk to comprehension, and the second one that actually executes the device. If we think about this from an ADAS experience, there may be one model that actually operates the autonomous features, the actual driving of the vehicle, and another one that's the interface between that system and the driver or the end user. So we have multiple models there in the NAND. So the first thing that has to happen is those have to be very quickly downloaded into the DRAM and then executed out of the DRAM by the SoC. So the key things here are really that latency to get the model loaded, as well as the overall interface between the DRAM and the SoC. And so in some cases you can see it's a simple model, in some cases these end up being multiple daisy chained. And so these are all system considerations that the OEMs and tier ones have to make. And ultimately it's about these system trade-offs, right? So what level of token rate are you trying to achieve? What level of quantization? How rich of a model do you want to be able to run? Are you willing to just store them all in DRAM so you can run them really fast? But then your system cost is going to be significantly higher because NAND is less expensive than DRAM. And so again, if this kind of fetch or store and download model works, it can be more cost effective for the overall system. So I mentioned this briefly, but again, just a little bit more detail in terms of what's driving some of these compute requirements and some of the overall systems. Some of these next generation solutions, very high-end vehicles, have pretty impressive infotainment systems in them, right? They have up to 32-inch screens for the rear passengers. They've got multiple screens in the front. So all of that IVI is driving significant bandwidth. There is also this in-cabin sensing. So again, I think we're all familiar with the outward bound sensors, right? That are looking for pedestrians, looking for road signs, looking for other vehicles, looking for the road. But there are also some of these that are internal, right? Whether it's a driver monitoring system for safety, am I falling asleep? Am I not paying attention when I need to be? Or in moving forward, there'll be some of that gesture recognition that will be more of that infotainment type of system. And for Gen AI even specifically, if we think about it, obviously Gen AI is also coming to mobile phones and PCs. And those tend to be single user experiences, whereas in a vehicle, there's often the driver, but some percentage of the time we have the other passengers in the vehicle as well. And so this Gen AI experience actually needs to interpret and identify different users and respond specifically to them. And in many cases, we'll have actually models tailored to those different passengers for the best experience. On the ADAS side, again, this is really about what level of autonomous driving are you trying to achieve. This top right is actually showing a graphic of projected levels of autonomy, level 2, level 3, level 4. You can see that the vast majority continue to be level 2. This graph's going through 2029. But you can see a significantly growing level 3 and ultimately level 4 set of experiences. And of course, both the hardware requirements as well as the security requirements and the memory and storage requirements go up by orders of magnitude as you progress through those experiences. Okay, so on the ADAS side is driving some extremely high requirements in the system. And of course, there's a SoC, power draw. Some of the systems that are going in there from various players in the industry are requiring enhanced cooling systems, air-cooled, even liquid-cooled, and really driving very high-performance compute. And all of that, of course, requires the memory and storage to go with that. Just to give some sense, this is essentially requiring multiple placements of this memory and storage hardware. So the memory, for example, again, going back to a mobile phone that we all carry around with us, typically only has one SoC. It may be 32 IOs wide, it may be 64. And in order to get the kind of bandwidth that these systems need, again, even for just level 3 in this 500 gigabyte range, are having to go, instead of 32 and 64 IOs wide, 512 IOs wide. And this just drives a whole complexity around the design system. I mentioned power, I mentioned thermals, of course signal integrity. All of these, right, become increased challenges for the overall system designer in that space. The memory itself is also having to evolve to some extent in order to provide cost-effective solutions that can achieve these bandwidths. Again, this is roughly, let's call it 5x what you would see in a mobile phone, to give you a sense for level 3 autonomous driving. And then if you're going to a level 4 or level 5, this is as high as a terabyte per second or 1,000 gigabyte per second type of bandwidth. And again, this is really driving limitations on the SoCs themselves that are going to do the compute. To have that many IOs interface to requires a lot of real estate on the edge of the die. And so this is essentially a limiting factor for many of these next generation designs. So they're really challenging the memory and storage providers to come up with new solutions that can achieve these bandwidths at essentially a smaller die edge for the SoC. So this is where LP5 is the predominant memory today for any new designs for automotive. It's also state-of-the-art for the mobile phones and for PCs. But quickly, you can see in order to achieve some of these higher bandwidths, looking for the next generation LP6. And ultimately, HBM, which is really a data center solution, is also being considered. Now you can see it really jumps off the page at almost 1.5 terabytes per second, so it almost overshoots on the system performance that it achieves. It's also, and it actually, it's not shown on here, but it actually, that single placement of say an 8 high or 12 high HBM in that space is still only, is maybe a 24 or 36 gigabyte of capacity, and the models that actually run are larger than that. So yes, you get the bandwidth, but you actually don't get enough capacity. So you need multiple placements of HBM, which is going to drive up your cost, which is also going to have challenges for thermals. And so we're looking at some alternative solutions in between there with whether this is processing in memory as a technology that's coming. It's actually very efficient to run some of the multiply, accumulate operations that are the fundamentals of Gen AI. And we continue to look at some other options that are still proprietary that we're not quite ready to show publicly that also could be other viable alternatives in that space. Okay. On the IVI side, again, this is really a trade-off that the system makers are having to make between how many tokens per second do I want in terms of the user experience is going to be most leveraged by that, as well as, again, how much quantization or effectively compression of the model am I willing to do. And so as we look at different options, you can see here that many of the common models that are out there are maybe like a 7 billion llama model, a 13 billion parameter llama model is a little bit at the high end. There's constant pressure for them, of course, to utilize and develop smaller models that can still give that experience. But again, this is all that model that has to be in the storage device, has to be very quickly downloaded into the DRAM and then executed. And the time target for that today is less than 1 second. In order to do all of that processing and be able to respond back. But ultimately, you can see that that's going to continue to drop in terms of the target threshold. I hear already from several players in the industry that they really want less than half a second, which means you have to double essentially that compute power as well as that memory and storage bandwidth capability in that space. So again, this is a roughly, typically about a 150 to 200 megabyte per second increase in the smart cabin requirements. There's all the other things that are still happening in the smart cabin. So this is that additional workload that's being in there. And you can see again, I won't go into detail, happy to talk offline, but the memory solutions that are being considered in that space, again, the selection of that is ultimately going to drive what the performance level capability of the system is, and therefore what the end user experience is going to be. So those were both for the memory or the DRAM. On the storage side, again, I mentioned that unless they want to just download all of the models and store them in DRAM and basically buy a bunch of DRAM, which is great for us, but at a little bit higher cost for the end user. Otherwise, the question is, can you store it in that SSD and basically just download it quickly enough? And so what you're seeing here, again, in terms of this selection of technology, I'll start from the bottom up, looking at the vertical rows. UFS 4, which is the standard in mobile phones today, and starting to gain adoption in automotive, I'll say within the next year. SSD Gen 4 is viable today, UFS 5 and SSD Gen 5 are the next generation technologies. And again, these are all trade-off considerations that these system designers have to make in terms of what overall capability do I want to ensure are in the vehicle so that I can get the best user experience in that space, and trade that off, of course, with whatever cost constraints are on that design. Okay, this is the last slide. So again, from our position at Micron, being able to essentially speak with all of the OEMs, tier ones, and SoC vendors in all regions of the world, we get a pretty good perspective now. That leadership is both a market share leadership, but also a technology leadership. And so one of the keys for us has been to really reduce the lag between when a new DRAM or NAND technology is available for say for data center or for mobile or for PC compute, and how soon after that can we have it also available for automotive? Because as you might guess, right, all of the things that we mentioned earlier, the security, the quality, the overall robustness, the temperature capability, all of that all has to be enhanced beyond what those other applications, what those other markets require. So there is additional development that we have to do in that space. But happy to report, and again, this is part of why a lot of the industry players are strategically aligned very closely with us, is that we have been first to introduce a lot of these historic technologies in there. On the top, we were first for the DDR4 and LP4. Most of what ships today in automotive is LP4 technology. All of the new designs have already moved on to LP5, where we also do have the technology lead. And again, the space on, I think with 2 sessions ago, there was a question around cybersecurity, and there are ISO standards, whether it's for functional safety is a key one, for cybersecurity, right? These are standards in the industry that are gaining wide adoption. And of course, we are able to deliver both DRAM and storage components that meet those standards, which can enhance the overall system capability and that robustness as well. Okay? So I think we still have time for questions with that space.
Yeah, I had a question. And this may be a little basic, but if you have an application-specific integrated circuit, as an end user, is that purely a hardware play, or can I customize it using software that I'm in control of?
It's essentially on lockdown. So at least all the systems that I'm aware of today are self-contained systems. Now, of course, you can download apps right onto your essentially center console and operate the app. So there's that aspect of it that's open-ended. But in terms of the functions within the vehicle, that's very closely protected with all the security policies that the OEM puts in place. Yeah, go ahead.
You're talking about level 5 in 2030, 2029. Isn't Zoox and Waymo taxi already level 5, or am I mistaken?
Yeah, so the question was around level 5, essentially availability out on the market today. Since we showed this slide, so that slide was only showing level 2, 3, and 4. It actually didn't, that graph, at least the graph didn't have a level 5 capability on there. You're absolutely right, that's out there today. I think but in terms of the percentage of vehicle units, it's still very, very small, so it doesn't show up on the graph. But absolutely, and those, those are cases where it's a little bit different dynamic on, of course, the requirements are very high for the performance at that level. But at the same time, the manufacturing model is a little bit different, where it tends to be, rather than a model running, let's say a traditional OEM may run for 5 years of vehicle in production, right? These tend to be a year or two. And so that opens up the door. I was mentioning earlier that HBM is not a great fit for automotive applications because of both the cost. But the other thing I didn't mention is that HBM almost overnight moves from old standard to new standard. So for example, we have HBM3E, that's the popular one today. HBM4 will be the next generation. Challenge with the HBM is that it's evolving so quickly that each generation is incompatible with the prior one before. And essentially, data center, as soon as the new SoC and the new memory to pair with it are available, almost overnight, all of the demand moves to the latest one, right? There's such a pull for that compute power. And so the volumes essentially go to zero on the prior technology. And so again, this idea of automotive needs a product for 5 years, it's not going to be there for 5 years because the new HBM's there. But for some of these level 5 implementations, they are that shorter lifespan, and so because they're more nimble, they're able to utilize some of these other solutions that might not be a fit for, in other cases.
Yeah, I have a question for you.
Where are you? Okay.
Yeah, so you talked mostly about memory, right? Both DRAM and NAND. I also wanted to know, how are you, in Micron's roadmap, do you have any combining compute and memory in a package or something like that? Are you looking at that? I mean,
yeah. So there's multiple ways to implement that. Of course, there are, there's a model a little bit like an HBM type model where the silicon and the compute. I should back up. Because the semiconductor transistors are significantly different for compute and for memory, they're essentially almost always going to be manufactured and designed separately. So they're going to be physically separate pieces of silicon. Now, having said that, right, there's different ways we combine them. We can combine them in package. We can stack them. We can put them side by side. And so you are starting to see some of those implementations. There are also, there's cases such as the Qualcomm automotive modules, the SIPs that they sell today, right, that are basically taking a packaged memory, putting that on a little daughter card, mini board, some of that implementation. So yeah, I think we'll continue to see some of those varying levels. The very, very tight level of integration for automotive is going to be a challenge just because of the additional robustness and testing that we have to do in order to achieve the higher quality as well as the higher temperature thresholds is very difficult to do at a wafer level. So it's not a complete, it's not taking that option completely off the table, but it will be a challenge to go to that full level of integration. So I think you'll continue to see a lot of these kind of daughter card implementations. And then the one other piece that I'll mention is, I did mention some of the PIM, the processing and memory. So I think there is an ability to do some limited amount of compute in the memory device. The advantage is you don't have to pass the data back and forth, which both takes a lot of time. It also takes a lot of power to actually do that. So again, it's going to be very simple applications because in a software stack, right, the ability of the software stack to now manage exactly where that data is residing and be able to pull it back is fairly complex. But I think all of those are options on the table, and you'll continue to see varying degrees of that integration. Yeah.
Thank you. Great presentation. Usually, my experience have seen global OEMs are very conservative in adopting much faster nodes with every generation and stuff. So can you comment on that? What's happening on the memory side, and what's OEM's reaction to newer technology adoption rates? Yeah,
I'd say that it's so part of my team is fully dedicated to validating our newest memory and storage devices with the automotive SoCs that are out there. And so we've gotten to a point in both the work that we do as well as the work that we do with those SoC vendors to essentially have that completed either as soon as our new memory and storage is out or as soon as their SoC is out, whichever one is kind of the new one into the combination. So that piece of it has actually gotten really efficient. So I would say today it's primarily a question on what's the lag time for them to get those new platforms to market for in those space. And that's where you still see that discrepancy, right, that range where particularly obviously China is very, very fast. Some of the other players are slower, but they are getting faster. So I can tell you for sure that they actively look for our help in trying to go as fast as possible. There's still a little work to do if they truly want to catch up to some of the other faster players, though. Yeah. Yep. All right. Last chance. Otherwise, I think we'll call it good. All right. Thanks, everyone. Have a great day. Enjoy your